thanks everyone for coming. I'm Mark Campanelli. I work at Rezanov. And I used to be at Workiva for a little bit more than 2.5 years. And I've been at Rezanov for about a year now. So I went to MSU and got my PhD in mathematics. So I am not a computer science kind of person. So please forgive me of any naive statements I might make. We build hyperspectral imaging systems at Rezanov, and so this is a little bit of my story going from mathy type software and numerics, which I still do some at Rezanov, to QA at a really big software company like Workiva, and then going to a very small company, locally based, where everyone's a little bit of a jack of all trades. So the agenda. I'll try to cast a wide net here to get everybody to understand what hyperspectral imaging is. Then I'll talk about some of the software development we do in Python for these hyperspectral imaging systems, or HSI systems. And then very briefly, I'll touch on how data analysis and machine vision / learning opportunities with hyperspectral imaging. I am not a machine learning person, so just an FYI there. My background is more in physical models, where every parameter in the model kind of has a really solid meaning, think like circuits and stuff like that. And a shout out, obviously, is that developing great products is a team effort, so there's a lot of people doing a lot of great things, and I am one small part of that. So also feel free to stop me if you have any questions along the way. So what is light made of? This is a picture of a typical solar spectrum. This little band of wavelengths here is what we actually see. Light with shorter wavelengths, which is basically a measure of its energy, has higher energy, and that's in the UV, so that gives you a sunburn, and it's also what a lot of insects see as they navigate around. Out here, with sort of decreasing amount of light in the solar spectrum, along with some bands here that are all caused by different molecules in our atmosphere. So this is a very particular spectrum of the sunlight, not the LED lights or halogen lights. Out here is the infrared, so it's beyond what we can see. But there's often a lot of information in the light that is out in the infrared. So it's UV for ultraviolet, visible for invisible, what we see, again, going from blue at 400 to 700, which is red. And then the near infrared is this really long band, which has a whole bunch of subbands, like short wave infrared, medium wave infrared, long wave infrared, and then far infrared, and then eventually you get out to microwaves, which start getting measured in microns. So how do we see light and color? Well, it turns out we have 4 different types of cells in our eyes. One of them is rods, which sees a certain band, and those are designed for your night vision. It turns out you see color a lot better during the daytime. And we have 3 cone-type photoreceptor cells that see red, green, and blue. And so, for instance, if something is reflecting light into your eye with some wavelengths in this area of the spectrum, your blue cone cell in your eye is going to integrate with this kind of response to that light. So if the light falls in here, that photoreceptor cell is really going to be firing. If it's out here, it's going to fire a little less, and out here even less. But it integrates all the wavelengths in here into one signal, which we usually put right at the peak. We think of it being at the peak. And likewise with green and red. I'm always surprised how narrow the difference between these peaks tends to be between seeing red and green. And so if someone's colorblind, usually maybe the red cones are all gone. And there's really a mosaic of all these cells in your eye, and that whole subject is fascinating. I'm not going to go into that here. But basically, you think of our eyes are reducing a whole bunch of information down into 4 channels and really only 3 for the color. It's really a weighted summation, that's all really integration is. And so it reduces the spectral information. So we're going to make a hyperspectral imaging system that doesn't reduce all that information, that spectral information. So there are multispectral imaging systems, which a lot of satellites have. So some of those like really cool satellite false color pictures you see, they break up the spectrum, including stuff that we can't normally see, into larger bands, right? So you get a little bit more information, but there's still a lot of sort of integration going on, reducing the spectral information down into only 4 to 12 channels. Here's a picture of a leaf. And these are different, like a whitish kind of region, a definitely red region, and a black region. And this is how those different regions here fall on a very coarse spectrum, if I think about it that way. And then there's really about more than 100, maybe even like 200 channels in here, which there's so many of them, we just kind of drew them all with a line, but there's really data points in here. But we kind of call that being essentially continuous, right? Because there's so much spectral information. And so you can see, yeah, region 3 is right here, which is pretty flat, and so it tends to look more white. I got a lot of these early slides from our marketing department, so hopefully they're technically accurate, but you're not always sure if that spectrum really is that piece, if you know what I mean. But anyways, these different shapes that you can kind of, they don't get integrated away over here. They can be very nice for classification and figuring out if two things are different, even when to your eye they don't look different. Here they look different for demonstration, but for like plastics recycling, there are a lot of like a 1 versus a 2 plastic that visually look totally the same, but it turns out in the infrared they look very different. Here's an example with pills. So visually, these pills all look white. Like right here, you couldn't tell that this pill is going to kill you, maybe, and this pill won't. But down here, when you look out in the near infrared, they actually have different signatures, and we've run this through our software with the classification algorithm, and you can start to see them apart. So hyperspectral imaging technology, there are a few different ways of doing this. You might think you just take a camera that normally sees RGB and just make it see 100 colors, but the way that works in the camera, there's actually like a mask that makes certain pixels on that camera only see green, and other pixels only see red, and other pixels only see blue. And you can only take that so far before you start to lose your spatial resolution, because the mask is reducing the number of pixels for each color to too small of a value, if that makes sense. So to get around that, we use a push-broom style hyperspectral imager, and that sacrifices one of the spatial dimensions in your camera. We use cameras typically about this size with a little monochrome sensor in there, sensor array. And it sacrifices one of the spatial dimensions to put those 100, 200, 300 channels of spectral information onto. And so the light would come in through a slit. So I don't know if you've ever done you make a slit with a grating and you see the rainbow. That's basically, we use a grating, and there's a lot more optics than this in there. That's where our secret sauce is. Light comes in, eventually hits this grating, so the spatial dimension is this, and the spectral dimension is going to be divided out this way. So this is going to scan across the sample and build up the image. But it comes, hits the grating, splits out into all the colors, so this dimension of the imager is what's picking up all these different spectral channels. So obviously this causes some issues if you're trying to image something that's moving very quickly, that's changing, right? You can only get a line at a time, so that is kind of a constraint on these systems. But in certain systems, they work just fine. In our benchtops or research systems, we have a scanner. Again, the light, usually we are illuminating, but the light is going this way into the camera. It's easy to think, oh, it's not really projecting anything out. But we usually do have an illumination coming from the side. And the illumination only has to be a line, actually, because that's all we ever see at one given time. So you can kind of really focus your light right down in one spot, and even do it with a laser, which I'll show you later. And then you move the sample relative to the imager. So this works well for conveyor belts, and also we fly them on planes. So that's this idea of the push broom, that you're just moving it across. The actual data comes out as data cubes, which, I mean, you might be used to like RGB or RGBA images with 4 channels. It's just the same thing, but it looks more like a cube because you have 100 channels. And typically, we implement it just with a NumPy ND array, and then we have metadata that describes what the frame rate was and all the other information about how you took the image. And that's a DIC that follows a de facto industry standard called NV. So here are a couple of those systems I mentioned. There's this more of a research design system. These get really hot. This is our illumination right here. So the sample is translating on the stage, and actually the light you image goes right up through the middle there into the slit, which is here, and then this camera right there I showed you is here on the back end. We are working actually on a new illumination system because you can be really efficient with your with your lighting. And these are so hot, I always worry if someone has like a wax candle there or something, it might just start to melt over time. You can touch these and almost burn yourself. So we're working on improving that right now. This is an outdoor field system, so a lot of times you're trying to look at vegetation in an area and determine if some of the vegetation needs water, that kind of thing. And you can, this is on a tripod that spins around. Different focusing. This is focusing usually at infinity. This has other focusing considerations because you're in the near field. And then we fly them on drones and on fixed wing aircraft, which I've been invited to go on, and I actually don't want to. They're like, he's kind of a crazy flyer. I'm like, well, I have kids, so. But it is fun to see them fly the drones around the property sometimes. And there's some great pictures of, they also have other fixed wing. There's actually, if you go to Rezanov, when you walk in, look up, there's a small remote control aircraft fixed wing. Kind of old school, and they launch these things out and they like shoot them. Like they don't fly like this, they don't take off like a normal plane. And sometimes that launch process goes very bad. There's a lot of expensive equipment that just has like a 1 second lifetime. Like when you see your rocket, Grant knows about this, when your rocket blows up with your $10 million payload. We're not in that realm of expense, but. So also for industrial sorting and classification, you can think of conveyor belts with, peanuts or what pistachios is a big one. Like you want to pick out any sticks that might have been in the mix, right? And that stick will have a different spectral signature than the actual nut that you're interested in selling. So obviously the conveyor belt goes by, we take the image, you have to be able to process this real time so that you can tell the robot or some air jet in the plastics recycling case will kick out, and then this, like, some will go up onto another conveyor belt or go into a bin, get sorted, that kind of thing. How am I doing on time? I think I'm doing okay. Grab a quick drink. So this one's a little bit of an eye chart. But I tried to summarize what is it like to work at Rezanov. Company's been around a while, 2002. I think, don't quote me on this, but doing more grants, that type of work at the beginning. Probably more SBIR, Small Business Innovation Research. I don't know if that's what that stands for, but grants for new businesses, that kind of thing. And some companies kind of just do that forever because they don't, they never necessarily grow out of that. I would say that we've largely grown out of that. We still do some really neat projects with NASA and DOE. And we have this new building on the East Gallatin River that has some room to expand. And that's kind of nice because you can literally walk to map through the park kind of from where we are. And I catch trout like right out front of the building. So we have 15-ish employees. That kind of goes up and down with interns and that kind of thing. Lots of different engineers, lots of optics and mechanical, not so much EE. And then we have 3+ people doing software. So we do sell products, right, to the general public. And so we have about a half a dozen of what I would say the off-the-shelf hyperspectral imagers right now. And then we also do a lot of custom integrations like those industrial sorting systems. Oftentimes you have to interface with their PLCs and to do whatever specific sorting you need to do. In terms of software development, it's a lot of Windows and Linux, not so much Mac. So we're a small company, right? We use Mercurial in Kiln, right? No Git or GitHub, which still causes me no end of headache because I learned GitHub first. Like there's this thing, large files in Mercurial, and that was what I was dealing with this week. Anyways, we use Fogbugs, and it was ClickUp, and I've heard people are moving away from ClickUp. I still like to use ClickUp for like planning out this microscope prototype that I've been working on. So no Jira, which I actually kind of like. We're at one location. I literally stand up and just talk right next to me. I do send emails to try to document things just so somebody can go back and remember what I wanted to say. But there's no HipChat or Slack, and that was one thing at Workivo was like, oh my God, can I just turn off HipChat? And you can, I guess. We're very Python-centric, down to our in-house BuildBot CI, so that's another thing I've been working on is we have to sign our software and we build it. Obviously the Kiln repo is, we use Kiln again instead of GitHub, that's off-site, but we build our own stuff. So yeah, no AWS or Google Cloud Platform, right? I think that's what that's supposed to stand for. We do make some Python extension modules, and we have a standalone imager-only API, which is in C and C++. I have not done a lot with that. I just worked on the builder for that, but not really on the code. We release on demand, and this is really just constrained by the ability to test all of our hardware. And we even have some legacy hardware that we don't really, like we have a legacy stage, and I don't think we have one in the building, but technically we still support it, and that always kind of keeps me up from my previous QA days. But so that is interesting. I mean, I used to think browser testing was hard, but like you can't keep a $30,000 near-infrared imager just sitting around trying to like run automated tests, and for our size that just doesn't really work. So, but I rarely take work home, which is super nice. So not hardly any like middle of the night calls or anything like that. This is our main flagship software, if I want to call it that. It's called Spectra. It's a Windows desktop app. It controls the imager and the stage. So when you're doing a scan, remember I said it's like line by line, so the image kind of builds up like that. It's like a waterfall display. I'm sorry, I don't have a video. This is an image that was already taken. It doesn't actually show the controls, but right here you're supposed to have like a play button to take a scan and say I want to take a 500 line image. And then this panel, when you're in scan mode, has these like a camera control and a stage control. So there is this kind of coordination, right, that has to go on between taking a line by line scan and moving the stage at the right speed based on the frame rate that you're taking lines at, in order that you don't get an image that looks like it's from the funhouse, right? It could either be compressed or kind of oblong based on whether if you don't get those speeds right. And right now this product, we usually have the customer put a circular target down and then adjust their controls for their light level. Usually the light is the big thing. How much light you have depends how your integration time will be, which depends determines your frame rate, which then determines how fast the stage has to go. That kind of makes sense. That's one workflow. There are other ways you can skin that cat if you just have tons of light. So this is our software. It also there's a free version, which any of you guys can go and download. I think we ask you to register. And that analyzes the data with various plugins. So we have a whole set of plugins. This is one, so there's like, you can't probably read these, but utilities, classify, analyze, color, I can't read that one, correct, I think that's for corrections. And then you can write your own Python 2 plugins right now. It's not the best documented system in the world, but you can usually go in and look at what we've already written. So that's kind of cool. I mentioned there's a standard format there. We also have to maintain a manual to help people try to use it, which hopefully people read, but who reads the manual, right? So that's another part of my job, though, is to make sure the manual occasionally gets updated. There's a whole build system around that. And then we maintain a downloads website, right, to download the manual. And it's pretty easy to use. Actually, I had a customer call the other day, and the phone eventually bounced to me, and I was cursing Spectra on that day, and he was like, I really like your software. It's way easier to use than their competitors. And it was actually really well timed. So I was like, phew. But one of the programmers, the early programmers who wrote it, I like to use the word kind of over-engineered, right? So like you can do some really weird things in Python, like rewrite the add and delete methods of something, and it just kind of went overboard a little bit in that. So that's some of our dirty laundry, at least is that how I see it. Let me do it on time. Oh, I lost my timer. There it is. I think I'm doing okay. So I'm actually converting Python 2 to Python 3 in Spectron right now. That's been one of my big things, and then that's required kind of redoing how our build system works so we can kind of build both in parallel and blah, 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 blah. So I do a lot of that stuff. But I've also been assigned this prototype microscope system. So we can also look at really small things with hyperspectral imaging. And this is, which I just learned this week as I was talking to Slater Kirk, who is the optical scientist who I work with, and he does all the optics. And I do pretty much all the software, and we work together, and it's been really fun. So a lot of credit to him. He told me that this is actually lily of the valley. This is a root cross-section of that, which we were using early on when we were creating this microscope system. We have one of these systems over at Montana Molecular, and they're doing fluorescence experiments, and we have another one that's down in Florida that's getting a little bit of a rework. And so we have those two kind of early customers, beta customers. This is about 20 microns in diameter right here, and it turns out the root has different spectral structure across, you know, going from the center up to the edge. There's some bands in here which are due to the optics that we're using, so I guess we should take this with a grain of salt. Our image is actually a little bit better now because we changed the filter out. But anyways, this is dichrome filter that kind of just cuts everything out right there. But we've since improved that. So it is very much a prototype system. And in this system, what's really kind of fundamentally different is there's this XYZ stage. So we don't just go linearly in one direction, but we can move it all over. And there might be an experiment where some parts of the tray that you're imaging are being treated with different nutrients or something like that, and you want to look at it over time. And then only 3 out of the 15 little, I can't remember what they're called, but the little places where the experiments are happening, maybe 3 of those in the long run are actually doing anything. So you might have a use case where over time you're changing where you are going to look at over time, and you might be taking a higher magnification look at it once you realize that that's the one that's lighting up, whatever mixture or whatever mutation you made to the little bugs living in there is the one of interest. So we need one of the goals was to, it's kind of hard to do that in Spectranon the way it's written right now. The front end and the back end in Spectranon are super coupled, even though there is this kind of, maybe you might say, over-engineered messaging system that handles everything. But it's really not decoupled enough and to do those types of experiments where maybe they don't even want a GUI, right? They're just gonna, just have some program that they need to come up with on the fly and then do some machine learning or other data analysis kind of real time. And you want to be able to, and I think maybe I should go to the next image. So we need to do that coordinated movements of that XYZ stage, which is more than we've kind of done in the past with our linear, just single axis linear stage. There's autofocus, those types of things. And here's a kind of a picture of that system. It's an inverted microscope stage. So this is the X and Y, and then underneath that is the microscope objective that you can't see, which the Z axis is its focusing mechanism. We illuminate only a part of the tray at a time with this green laser line. So this is a fluorescence experiment. So you shine green light on a certain type of really fancy protein, and it absorbs that green light and re-emits it in a red light. Now again, these are all spectra, but mostly it's red, mostly it's green to start. Well, for the laser, it's really narrow. For red, it's a little bit broader. I think I have a picture of it maybe later. You kind of saw it on the root. They look very similar to that root slide. So to do this whole tray, you can like serpentine sweep along the tray, right, to be able to measure the whole tray. And often they have like grad students looking at these there's things growing on that tray that you can't really see, and you'll see it later. And you know, they're looking at it with a point spectrometer and some funny glasses, and it's really painstaking. So the idea is to like be able to scan through this tray, even if you did it in an hour, it would be like a huge time speed up for their process, and hopefully they can graduate in 7 years instead of 8, right? I have this, since I went through grad school, and the grad student that works on this, I'm always like looking out for her, like, they're like, it's okay if it takes her a little while. I'm like, no, it's not. You remember, you know, some of you have PhDs too. So then this is the bacterial culture tray. So you grow it up in that goo, you know, basically it's nutrients that they can grow. And then there's a reason it's black, which is to avoid, I think it avoids a lot of the background fluorescence, which can be a problem. We light up this region. That region goes through a whole bunch of optics that kick it back out, and eventually comes out as mostly red light when they fluoresce, and goes into the imager right here. This is one of our imagers. This is a more high resolution visible near infrared imager, so about 400 to 10,000, 4,000 to 1,000 nanometers. This is the stage, I already said that. This is some of Slater's secret sauce and my colleague. We have there's beam shaping optics in here, so the laser comes out as this sort of Gaussian, you know, cross section curve like this, and we need to make that into a line, right? Because we want to shine all that light right on the same line that the imager is going to pick up at the slit. So this line gets imaged at the slit there. And then this laser source, this particular one is 532, which is greenish. It's not really on right now. And then there's a danger signal there. And you can see the laser, so it's not as dangerous as some of the like near-infrared ones where you don't know you're frying your eye. But I had one day, I went out to lunch with my wife, and I think I went from just dark to light, and I was seeing like these weird spots, and I was like, oh my gosh, I literally was freaking out. I'm like, oh my God, I think the laser must have hit my eye, and I didn't realize. It didn't happen, but you do have to be careful. But it's just a joke, right? Like, I'm a mathematician by training, and it's like, oh, my fingers are so rough from handling all the numbers today. These first world problems, right? Best type to have. So now I'm kind of going to get into some of the, again, not a trained computer scientist, but some of the things I've learned now having to integrate more hardware with software. I had done data acquisition in the past, that kind of stuff with LabVIEW, but this is where I really jumped in hardcore with Python and tried to like work with hardware with Python, which has been interesting. So, so I say desktop apps are so straightforward, right? Except when you have hardware, maybe. And I actually heard this in a different talk. Like the network, you know, hyperspectral imaging hardware isn't homogeneous. We have different types of cameras, different types of imagers. They all have like little design differences, right? And it's not 100% reliable, right? Your user can always unplug the camera at any time. That's one big thing. Again, fairly rare because they don't want to screw themselves up, but these things happen. So, so this is kind of like, I talk about like bargaining with the hardware. So so I had to come up with a way to get the aspect ratio of my images coming off the microscope right. So I have to know like the speed of the stage and how much light's available and what the frame rate is. And I'm like, okay, I can calculate this just perfectly. I figured out how all this mechanics works. And this algorithm needs precisely 56.76 frames per second. So Hal, set the camera to that, please. I'm sorry, Dave, I can only set the integration time. So it turns out some cameras, you can set one, but not the other. And then sometimes it's a limited range. Or it depends on the gain you've set on the camera, right? So you have to take all that heterogeneity and put it into like a common API. And that can be challenging. And also the user happened to reconnect the camera, so all that state you had just set up on the camera is now gone. So you kind of want to, this is a very extreme example, but the similar idea comes and can kind of cause you some headaches. And if you didn't know what I was referring to with the network, this is from the Fallacies of Distributed Computing, which is always worth a read. It's really for distributed systems. Although I saw something else when I was preparing this that said that those are no longer an issue in today's modern world, but I probably disagree. Okay, so here's I had to throw some code in here, and this is kind of new for me actually. I usually do during mathy talks where people start throwing up at the equations. So you can throw up now at this eye chart. I do hope that slides are available. It's warts and all at this point. This is very much a prototype. I have not released like version 1 of our API yet. But again, my 2 use cases to keep in mind here is the Montana molecular people. They want me to, I wrote a GUI dashboard, which I don't discuss in this talk. But it's a simple GUI dashboard for doing these microscope scans. And the idea is they get the data and then they put it over into Spectra, and they load it into our regular software. And I've written then, they've kind of offloaded me to write the analysis on that as well. And I'll show you some results of that at the very end. And then the second use case is no GUI really needed. They have some other developer who's doing fancy machine learning stuff, and he needs a really nice back-end API that he knows I can say, tell the stage, go here and rescan this for me again, and 5 minutes later I'm going to tell it to do that again, and I don't want you to lock up my whole system while I'm waiting for the next scan to come in, that kind of thing. That makes sense. So dealing with this bargaining with the hardware, you may or may not know that in Python, oftentimes, like the new way, you'd say, with this file, I want you to open it, and then I'm going to do some stuff, and it will take care with that context manager. No matter, like if you throw an exception during that, it will always close the file, at least as best it can when you're done. Right? So you can write your own context manager, use this decorator, and for me, I have a camera context, which there are different sequences of things I want to do with the camera, and if every time you have to kind of make sure the camera was open and didn't get closed by accident before that. And maybe I'm doing 3 things. Maybe I'm only doing 1 thing, which that's a pretty easy thing to do. But maybe I'm doing 3 things, and I don't want to close and reopen the camera each time, because that starts to become inefficient, or lose whatever settings I just set when I close the camera. And every camera acts differently, right? So I realized I can write my own context manager. I can send it in my requested scan parameters, make this the frame rate. Blanking on frame rate's a big one. What's the gain? That's another big one. And then it's going to go through, it's going to check that it's open. If not, it's going to open it and then close it if it was closed to begin with, et cetera, when it leaves. And it's going to bargain with the hardware, and the hardware is going to go, I can actually give you this frame rate. And again, the deltas are usually very small. If you read through my long description here, I mean, we're not talking about huge deltas typically, but when I record the metadata for that data cube, I want to record what it actually set the frame rate at. Or maybe the GUI, when they're going and sliding, I'll actually put the actual frame rate that it gave you, even though you requested something else, right? So little things like that. So basic context manager. This was new for me. Again, I'm a little bit of a neophyte in this stuff, so this worked out pretty well. It still needs to be fleshed out a bit. I do want to point out, I actually really like in Python 3 these required keyword parameters. So that means you have to name every parameter that you pass to it. You can package that up in a dictionary and then double star it and send it through really easy, which is also really nice. And then just watch out for the default values. And I really don't like default values because they actually become part of your API, and you change your default value later and you break people. But I will point out, you don't have to actually have the default values here. I just happen to have them all in this particular example. So this is a pretty low-level function, and you get your actual scan parameters back. Here's how I would use it. This is still not part of the exposed API, but it's a common configuration call you're going to call on the camera. So you wrap it in a try. You're going to say, with this camera context, where I have some requested scan parameters, it's going to spit back what I actually could set, which is close. And then I'm going to, I mean, this one is pretty basic. It's just doing a configuration. And you notice this is, I kind of like to return dictionaries as well. I think there's a performance hit for doing that, but we're not doing anything crazy right now. So yeah, so just using context managers kind of abstract that way, and this is really helping other developers kind of not have to worry about it. You might also know, or you may or may not know, that you can do these with locks. You can put locks in with statements in Python. And for the low level, you never want to tell the serial thing to start doing, ask it for some other, this is in a stage usually. You don't want to tell the stage something else while you're still waiting for a response, so you usually put that lowest level read write in a lock. So that's where that came up as well. Okay, trying to wrap it up. I'm actually getting fairly close. So, so the main architectural design goals for this microscope was, like I said, enable the GUI-less operation by a more friendly Python-based scanner backend. Right now, we can only run the imager with the C++ API. There's no coordination with the stage. If you have your own stage, you kind of got to figure that all out. I want to automate the tasks, especially doing that serpentine sweep to get the whole tray, synchronizing that and getting your aspect ratio without having to futz around with the sliders until it's just right. I want to free the API consumers from the hardware implementation. Obviously, they shouldn't care which particular imager they're using. I want to accommodate the common user workflows. So that's, like, what are they going to do? They have to go to scan this area on the tray, then this area, then here, then do a focus, and then there's a whole set of calibrations you have to do to make sure your data are comparable, and I'm not going to get into that. And then ease the pain of concurrency, right? Concurrency is hard, both for the consumers and the developers. So in terms of the, so someone will say, Windows plus Python, right? It's clearly not a real-time control system, and I'm trying to coordinate hardware and frame rates and all that, and it can still get, it can bite you if you don't do it right, or if things are just getting delayed. And then, maybe a Python skeptic or hater will say, but what about the GIL? So that's the global interpreter lock, which means you can only basically have one thread running at a time unless you do really fancy things. But Python is a natural choice for data analysis and machine learning, right? The whole TensorFlow and all that is very Pythonic. And that's kind of the whole purpose here, right, is to get data and make decisions. And Python's great for that. So here's what I kind of came up with as I was learning about multiprocessing in Python. And I decided I would have a parent process, which is where the API lives in the scanner class. And then I would just have, basically, for each hardware chunk that I needed to run, I'm just going to spawn off a child process for each of those. So there's these 2 child processes, which the user of the API does not have to worry about. There's basically a remote procedure call, duplex pipe. So when the scan wants to start, it can send signals to both these guys that, oh, you're about to start a scan. There is locks on those because you don't want to, start another scan while you're in the middle of a scan. So that's like a high-level lock. You might want to kill these guys at any moment's notice, like the stage is about to crash or is crashing, so you have to be able to send a kill event in. There's low-level communications in each of these guys, and its only purpose is to just manage its hardware. And there isn't 1,000 of these things that I have to manage. There's only, maybe you'd have a shutter in here too, which would be another third process. Eventually we'll probably have that. But they each just kind of do their own thing, one purpose. And you send these remote procedure calls in from the main API, like scan this area of interest. These guys have to coordinate with each other, so they actually have a pipe directly between them that enable that very fast communication. They don't have to go back through here, which maybe this thread is locked now because you're doing some data analysis while you're doing a scan, right? So you want to have that direct pipe. And then there's some other smaller pieces here. I return a future here to when this is a IO bound type of process. So eventually this will resolve just like a promise in JavaScript. And so there's an executor thread that's a Python thing. It just kind of, you submit the job. I think I have another example on the next slide. And then there's shared data. So what's my stage location while I'm in the middle of the scan, or what's my frame rate right now? It beams those observables as data flow right down into this shared data process, which this guy can observe. And then the data cubes itself are coming off as frames off this process, which are going into a NumPy mem map, which got me out of doing a whole lot of hard work. And then that data can be observed again, so you can update the screen with the data cube as like a waterfall as it's getting. So that's what I came up with. There's probably something a lot better, and you can tell me afterwards a better way to do it. There's some limitations, and actually how I implemented a very, very naive RPC in Python I thought was kind of fun, but also dangerous. But dangerous if you abuse it. Okay, so but Python has futures. I think some people really don't like how they did it maybe, but so basically I have a scan with stage. This is part of the exposed API. There's some setup it's going to do, basically make sure that data cube is there to start. So in the future when this thing eventually runs, it can find it. And then this is delayed or deferred. And you return a future which comes back out of this future executor. So that was that thread in the main thread, in the main process. That doesn't do much, but it does monitor and wait for the return values from the RPCs when the hardware is done scanning to come back and have your result. So the data cube is getting written and you can always observe it, but eventually it's going to tell you I'm done and I didn't have an error or maybe something went wrong. So that's this kind of job solution. So this was all new to me too. I'd never done anything this fancy in Python. And concurrency is hard. And I already mentioned that NumPy, we think, is robust enough to actually get around some of the shared memory with what do you call ring buffer, right, that we're doing in Spectra. It's a lot can go wrong with that. Okay, I'm almost done here. I think I'm probably over time. It says I have a minute left. So now I'll talk a little bit about data analysis again. I'm not a big machine learning person, but hyperspectral imaging, enables richer image analysis because you just have richer data. Some of these data cubes off this microscope system, although this is a little bit unfair, but they can be, gigabyte sized. We don't really use all the wavelengths in there. The fluorescence spectra are really in a fairly small band, so I'm over-exaggerating there a little bit. But just to get an idea, if you have a grayscale image of a typical rectangular image size, grayscale will only have one channel or band, right? And you're going to get this many elements depending on whether you're what do you call that? The dynamic range, right, of the A to D converter, right? We usually don't get into 64 bits, but you can be anywhere in that range. So you got to multiply to get the actual sizes. But the number of elements is what's key. And you can see this like 2 orders of magnitude jump when you have tons of spectral information. So that becomes an issue. And from my brief, we had a customer that we were doing some food quality stuff for. And so I did a brief foray into some of the machine vision and like really classical machine vision, just like segmentation with oh man, I'm blanking on it. Maybe I should come up with. Anyway, there's traditional ones and then more like machine learning based newer methods for segmenting images. You know, oftentimes the first step in those is if you have a color image, make it grayscale, right? So we don't really want to do that here. Like we have all the spectral information, we're supposed to be using it. And so here's an example of how you can use that. This is one of those microscope trays that we scanned, and they make, Montana Molecular makes these, I don't know how much I should go into it. Basically, they're trying to make things, make markers for biological mammalian cells. So it's a whole interesting story about how they grow these things up in E. coli and they try to mutate them and make them be different colors so they can mark different biological things happening on a very microscopic level. And then they eventually attach it to something in the membrane of a muscle cell so that when an electrical signal goes across the cell because the muscle is moving, that it will light something up. And you want to light things up in different colors. And obviously I'm not doing it justice. It's really much more complicated than that. But so they're taking a basic fluorescent protein that they attach onto these different parts of cells, and they're trying to shift its color one way, or like blue or red shifted. And this is one of those images from, like I said, that tray that we lit up with the green light. They fluoresced in red light, and the fluorescence kind of looks like this, and its peak is definitely in the red. And that peak will move around based on how they've mutated the bacteria. And so I was able to use the spectral angle mapper, which is basically, you know how you learned about the angle between two vectors in 3 space? Well, an RGB image is one of those vectors in 3 space, and a 200 channel hyperspectral image is in 200 space, and there's still an angle you can define between those. So you can look, and sometimes these guys come out green, like they didn't mutate properly or they didn't filter them all out. Those immediately get filtered out because their angle is like this, right? Green to red angle is like this. But all the ones that you're interested in, the angle is really small between them. So I just look at which, and they don't overlap often. They often get good spread, so I don't have to worry about 2 different colonies and separating those so much. So you're looking at the ones that are close like this. You filter all those out, and then you just look at, there's different ways you can analyze the shape of this distribution or just where the peak is. This is just looking at where the peak is, and then I kind of false color how much the peak is shifted from 598 to 591. It seems like a small shift, but that's just kind of a really nice shift. And so like this guy here is the most red shifted, and these are various degrees of more blue shifting. And then the graduate student, who hopefully I am saving some of their time for their hiking or whatever else they want to do that's fun, they go in there with a toothpick and say, I like this one, and I'm going to put them through the cycle, the game of life again, and then see if we can't make it shift even more red, and then pick the most blue one and see if they can get to shift more blue. So no fancy machine learning there, but a very simple tool. Just the angle between 2 vectors enables you to do pretty crazy segmentation. So I think I did relatively okay with time, maybe not as much for questions.